Preparing to live stream, setting up your meeting, redirecting to YouTube. All right.
1 minute.
So. Testing, Allie, can you hear me?
Yes, I can.
Great. So why don't we let them in?
All right, off we go.
Welcome, welcome. This is Science Distilled, the Science of Winter. Welcome, everyone. We are looking forward to hearing 4 speakers on the science of winter. We'll be getting started in just a moment. If you're with us and it's snowing where you are, tell us in the chat how many inches you've got so far outside your house. Tell us if it's accumulating and how much.
5 inches.
Oh my gosh.
And more coming.
Coming, that's right. Okay. Welcome, everyone. We are so happy you're here. This is the first Science Distilled virtual edition of 2021. We have got 4 amazing speakers lined up for you tonight. I am Megan Collins. The topic of this event, the science of winter, could not be any more timely for this region. Joining us tonight are 4 experts on the science of winter, each of whom looks at the topics of snow, ice, weather, climate, and all things winter from different angles. We will hear those perspectives tonight, and we would be remiss if we didn't take a deep dive into atmospheric rivers, which is the name of the type of storm that we are experiencing right now in the Sierra Nevada. A couple of Zoom etiquette tips. You can keep yourself on mute the entire program. Our speakers will be unmuting themselves to speak, and this will just help reduce distraction. So we really appreciate that. You can pin our speakers by clicking in the upper right-hand corner, the little view button. So you can pin the people that you want to hear the most. And we are going to be taking questions at the end of the talks through the chat. So at any point in this program, you can enter your questions in the chat box. We will also be taking questions from YouTube, so feel free to put your comments, your chat in the comments box, and we'll also be checking those out. So I see some familiar faces on screen. So glad to see you again. If this is your first or your 15th Science Distilled, we are so glad you're here. Science Distilled is all about sharing the great science that is happening right here in this region with you and introducing you to the great people behind this great work. So this event is co-hosted by the Terry Lee Wells Discovery Museum in Reno and the Desert Research Institute. I am with the Desert Research Institute, and we are the environmental research arm of the Nevada System of Higher Education. Our science drives solutions for a changing planet. I would like to introduce Patrick Turner now, who is my co-host, and he's going to tell us a little bit about the discovery.
Hi, Megan. Thanks, everyone, for joining us tonight. We're really excited to bring yet another Science Distilled to everyone out there. Very timely topic tonight. For those of you who aren't familiar with the Discovery, we are a 67,000 square foot hands-on science museum located right in downtown Reno, Nevada. If you haven't visited, we hope that you will very soon. We offer a wide range of exhibitions that range from the interests of Da Vinci to human anatomy, so that we hope you'll come check us out, and we hope you enjoy tonight's presentation.
Thank you so much, Patrick. Let's get into the details. So our hope tonight is to unpack the science concepts behind some of the really common terms that you hear in weather forecasts, climate discussions, or all things snow and ice. So we're going to do that by taking a long view. First, take a long view of the history, and we'll look at some science that's actually done with ice cores. And then we'll look at the very cool phenomena worldwide that help scientists understand our current weather. And we'll end with a view on atmospheric rivers and what is actually possible when it comes to seasonal predictions, kind of the holy grail of forecasting. So please enjoy these 4 unique perspectives tonight. First up, I'd like to introduce Nathan Chelman. Nathan will give us a look into the past and how it helps inform future forecasts. So I'll just share my screen, and Nathan can have a go. Can you hear us, Nathan? Let's see. Nathan, you might be on mute.
Hey, Megan.
Megan,
Yes.
it
All
looks
right,
like, go ahead.
I'm on a different name now, Megan. My computer decided to install Windows Update.
Yeah.
So timely.
Yeah, a little suspicious. Can you hear me okay?
Yes, we can.
Okay, so good to go. Thanks, everyone. Sorry about that. My first major Zoom disaster there. So tonight's program is focused on understanding winter from a number of perspectives, from looking at forecasts, trying to understand individual storm events, and try to put different storms and different winters into context in the greater, bigger picture. So my work focuses on using ice cores to do long-term reconstructions to try to understand how climate and Earth's atmosphere has changed in the past. So we can go to the next slide. And so we'll start things off with a poll here. It's pretty quick. The simple question is, how old is this patch of snow or ice? You can see 2 pictures of it here, one from 2016, one from 2018. This is the same patch of snow and ice. It's up in the Rocky Mountains. And you've got 4 options there, ranging from 1 to over 10,000 years old. And you know at least it's 2 years old, so that's a good start. We'll come back to this towards the end of the talk.
Okay, about 40% of people have voted, so we'll
That's pretty good.
another minute. Yeah. All right.
All right.
Vote in 5, 4, 3, 2, 1.
Time's up.
Cool. So keep going here.
You see the slides?
I'm still on the poll for some reason, but if it's
Okay.
changed.
Hold on. All right, so we're going to share the results. You all can see it, and then we'll
Okay.
get
Oh, wow. Surprising. That's interesting. Okay, good, good. Well, we'll have something to talk about here at the end.
All right. Now, are you back on the slide? You back on the slide?
No? I still see the slides, yeah.
You still see the slides or
Yeah.
the poll?
We can go to the next one.
All right. hold on, I'm sharing again. Okay, here we go. Thanks for bearing with us.
All right, perfect. There we go. So when I'm talking about ice core research, I love to show this animation because it's a really excellent illustration of what ice core research is all about. So this is an image based on satellite data looking down on Earth, and you can see what's swirling around in this picture are aerosols, which are airborne, tiny little airborne particles and chemicals. And these aerosols in this image are color coded. So you can see dust is coming off the big deserts of the world in orange. You can see that coming off the Sahara in the Middle East. You can see in green, kind of in the rainforest, you can see burning emissions, so from wildfires and from agricultural burning. In white, you can see sulfates. That's primarily emitted from human activities, from pollution. And so you can see there's a lot of sulfates coming off of densely populated areas, such as the northeastern US, Europe, and then also from China. And then in blue is sea salt, so sea spray getting whipped up by the wind. And what you can see in this animation is every once in a while, these plumes get transported up and over into the polar regions above Greenland and Antarctica. And then when those chemicals are above those polar ice sheets, the chemicals fall down to the ice with the snow and are preserved in layers going back thousands and thousands of years. So you can go to the next slide, please. That image was based on satellite data. And so satellite and observational data are crucial for making forecasts and to know what's going to happen in the weather in the upcoming days to weeks, and for looking at what's going on in modern times. So you can see the satellite picture on the left is giving you a really detailed big picture of a winter storm impacting the west coast of the United States. And then to complement satellite data, we also can use observational data to understand what's going on closer to Earth's surface. So this image on the right is a monitoring station specifically designed to study snow. It's the SNOWTEL station. There's a bunch of these stations across western states in the US that's used by water resource managers to predict runoff in the spring. So it has a snow pillow, which essentially weighs the amount of snow on top of that pillow, letting them know how much water is in the snowpack. And it also has a bunch of other specialized sensors on it for studying snow. And so while satellite and observational data are really crucial for knowing what's going on in recent times or in the near future, we can click next, please. If we want to know what's going on earlier back in time, it's a little bit more difficult, just solely based on observations and satellites. So satellite data goes back a few decades at most, and depending on how you define an observation, they can go back a couple of centuries. But what if we want to go back earlier in time and know what was going on prior to these eras? So for example, I think Ben in the next talk is going to talk about how recent snow droughts have compared to droughts from 1,000 years ago. So how do we actually know for sure what the droughts were like 1,000 years ago? Next slide. So in order to go back farther in time, we need to turn to landscape features that record environmental change. And so a couple examples of this are trees and lakes. So for example, trees, each year they add a growth ring to the tree. And depending on the growing conditions of that year, the ring might be small or large. For example, if it was a really bad drought year, the tree might not be able to grow that much, so the ring would be very small compared to the others. Similarly, lakes record environmental change from the landscapes around them in the chemicals such as pollen and charcoal that are deposited on the lake floor, as well as the shorelines that the lake can actually etch into the surrounding landscape, letting us know how high or low the lake level was at any given time. But since we're doing a winter-focused topic here, I'm going to talk about something a little more wintry. Next slide. So one other way we can go back in time is to use ice cores. And so based on that animation you saw earlier, those chemicals in the atmosphere are deposited on ice sheets layer after layer, year after year. And as that snow builds up, it's compacted into ice, and those chemicals are preserved. So by taking samples from either a mountain glacier, like you see here on the left, or from an ice sheet like Greenland, which is a picture here on the right, we can essentially go back in time and reconstruct what was going on in the atmosphere to get a bigger context than outside of our instrumental and monitoring time ranges. Next slide. And so in order to actually get an ice core, we have to go down through the ice to go vertically to get a profile. And so to do that, we use an ice core drill, which is what's here on the left. So you can see the sharp teeth at the bottom that actually do the cutting. And the drill cuts itself down around an ice core, which ends up in the center of that drill. You can just see it peeking out there. And so the drill goes down about 3 feet at a time. Every time it goes down 3 feet, you bring it the whole way back up to the surface and push out the ice core that's on the inside. And if you've done everything right, you end up with an ice core like you see on the right here, a nice pristine ice core. Next slide. And so Greenland, and when most people think of ice core research, they think of Greenland and Antarctica, and rightfully so. We get our best, most detailed ice core records from these two ice sheets. Next slide, please. And so just to put in context what kind of information we can get from ice cores from Antarctica and Greenland. From Antarctica, where the ice can be over 2 miles thick, we can get the longest continuous ice core record of about 800,000 years. And then from Greenland, the ice is also 2 miles thick, but the records there tend to be shorter. So the longest records from Greenland are just over 100,000 years old. And so you can see, compared to what we have from observational and satellite data, these really give us a much bigger temporal context for what's going on Earth. Next slide. And so I also mentioned the potential to use mountain glaciers for such similar reconstructions. So mountain glaciers aren't as remote as Greenland or Antarctica, so you can learn more about specifically is what's happening in a more local geographic region if you take an ice core from a mountain glacier. But because they flow relatively fast and are subject to more melt processes, glacial ice core records tend to be quite a bit shorter. So next slide. And so most mountain glacier records are on the order of a few hundred years, with a few reaching back a couple of millennia. So these are the 3 main archives we go to for ice core research to reconstruct what was going on in the atmosphere. But let's circle back to that poll now on the next slide. And so this is the picture I showed you at the beginning. This is a little ice patch that I've begun to start studying with collaborators. It's up near Yellowstone National Park. And so I was actually invited to sample this ice patch by a bunch of archaeologists. They were really interested in studying it because they found a lot of artifacts melting out from around the edges of it. So they invited me up to their sampling site. They actually had a handheld ice core drill that they were going to use to take a profile. So for the next slide. And so we went out on the ice patch. It's about 2 football fields in surface area, just to give you some context. We took the handheld drill out there and started drilling. And right away on the next slide, you'll see a picture of the ice core we got, which looks a little bit different than that one I showed you earlier from Antarctica. So this one here has these big dirt layers going through it, which if you've done something, as an ice core scientist, when you see a big dirt layer in your ice core, you really worry what you've done wrong because there's not supposed to be dirt in the middle of an ice core. But it turns out that these dirt layers are the key to understanding this ice patch, because inside of those dirt layers is organic material like grass and leaves, and even little twigs. And using that organic material, we can use a technique called radiocarbon dating to get really precise, accurate dates on that material in those layers, and therefore constrain the age of the ice in between those layers. And so next slide. And so it turns out, this is the only graph I'll show you tonight, that ice patch where we cored it was almost 6 meters deep, so about 20 feet deep. And there were 30 of those organic layers. So on the left, in that graph on the left, those red horizontal lines are each organic layer. You can see 30 of them. And on the x-axis going horizontally is the age of each layer. So you can see those blue dots getting older and older as you go deeper and deeper in the ice core. And the very bottom of this ice core, just 20 feet down, was 10,400 years old. So we can go to the last slide. And so to answer the poll question, it looks like a lot of people actually guessed 1,000 to 10,000 years, which is really surprising because when I first saw this thing, it just looks like a drift of snow left over from last winter. If you were hiking by, you wouldn't think twice. When we were coring it, there was some guy out there skiing on it who was trying to get turns every day of the year. So he comes up to the ice patch. He could have gotten turns for 10,000 years, it turns out, just based on this little thing. So that's all I've got for you tonight. Thanks for tuning in, and I hope you guys enjoy the next 3 talks. And apologies for the technical difficulties there.
You did great, Nathan. I bet that guy is in really good shape. That's all I have to say.
For sure.
Great. So next we have Ben Hatchett. Ben is an expert he studies extremes in our climates and weather. And he's going to tell us about some of the extremes over the medium term, where Nathan just told us about the long-term. Ben's going to tell us about the medium-term in our region, and that's going to cue us up to understand the present. So, Ben, it is all you.
Cool. Thanks, Megan. And thanks, Nathan, for excellent introduction and showing some nice older snow and ice. So our landscapes around us, places that we like to recreate or photograph or just spend time in, are awesome indicators of the kinds of weather and climate extremes, the weather and climate variability, and longer term change in individual weather events, and notably in more longer term climatic change. So the things that we look at around us really have a lot of keys to things that go on, and that can take place over a variety of different timescales depending on where you're looking. So Megan, if you can go to the next. So one really nice example, and Nathan introduced a variety of different paleoclimatic indicators. The pluvial lakes of the Great Basin, which are these things I like to think of as natural rain gauges that rise and fall with wetter, drier climates, are a really fantastic way to document just how quickly the landscape can change in just a few years. So this is a view of Honey Lake, which is just north of Reno. And prior to 2017, there was basically no lake following a rather persistent drought. And then after 2017, the lake filled back up. And then again in 2019, the lake got even a little bit higher. And so it showed us just how rapidly these lakes can respond to climatic changes. Next slide. And there's other changes that are ongoing in our environments that are reflective of myriad processes operating over various timescales. But one odd thing that I've been experiencing is that we're really starting to see some rapid change in a lot of our favorite environments. And now I have charcoal all over my ski clothes and my biking clothes because a lot of our favorite places to recreate are changing very quickly. And as they change and dry out, they tend to catch on fire a little bit easier. And so that makes for an interesting place to look at and think about all of the different factors that are driving these environmental changes. Next slide. And we can really just look back at the last decade or so, and we've kind of seen a variety of, or really the bounds of just how extreme the climate can be. We've gotten little snapshots of it. We've seen 4 extremely low snow years. The 2015 year was the record low in our historic records, and there's some work that suggests that's one of the lowest snow years in approximately 500 or so years. 2018 and 2020 were both pretty close to 2015, but we got lucky and those got rescued late in the season by a few spring storms. The current year was on track to actually be worse than 2015 in the southern Sierra Nevada, but hopefully we come out of that one and then keeps snowing and keeps us from seeing another very poor year as far as the snowpack goes. The 2012 through 2015, kind of that core drought period, those 4 years gave us a taste of what some of these extreme drought periods that last really strongly took place in our region during the medieval time. So when Beowulf was being composed around between 900 and 1200 AD. And those were several 100-year-long droughts, but they had similar precipitation declines to what we just had in just over a 4-year period. So you can get an idea of how rough things would have gotten if our 4-year drought extended for 40, 100, or 200 years longer. But a key thing to keep in mind is that even though those were similar in terms of how dry they were with regards to precipitation, things are warmer now, and that's really exacerbating challenges associated with these droughts. The other thing that we're starting to see a lot more of, and more in an extreme sense, is this weather whiplash, where we go from really dry to really wet, back to dry and back to wet. And basically almost every year, with the exception of 2016, was either really dry or really wet. And 2016 was interesting because it was supposed to be really wet. That was the Godzilla El Nino that Dan will talk a little bit more about in just a little bit. And so we've seen a lot of indicators that really point out that variability is a hallmark of our region, but the pendulum is swinging more. We can go from 2018, where we had basically no snow in the middle of winter, and then the next year you have chairlifts becoming buried. Next slide, please. And it's this millennial perspective that really helps us get an understanding of where we are and where we're going and what we need to do to be able to adapt to these kinds of weather and climate extremes, where we go from this record dry period and then just a couple of years later, we get a taste of just how wet things can really be. So I mentioned that 2012 to 2015, or you could even extend to 2016 drought was about as dry as these medieval mega drought periods were. And then 2017, which I mentioned, filled up a lot of the pluvial lakes of the Great Basin. That's an example of how wet it would need to be consistently to fill up the lakes of the Great Basin back to their deglacial high stand. So when those shorelines were formed several hundred feet above the present day lake levels, if you drive around the Great Basin and you look for bathtub rings, that gives you an idea of just how much water there was. For example, if you're hanging out in Levining in the Mono Basin, at the end of the last ice age, at about 17,000 years ago, the water of the lake would have been more than 300 feet above you. So we can use these examples to really give us an idea of just how extreme things can get and the persistence required to drive those extremes. Next slide. And a key source of this variability comes from having too many or too few large storms. The majority of our interannual precipitation is explained by our wettest storms. And we usually explain these storms in terms of the term atmospheric river, which really just means a mid-latitude cyclone that is associated with a plume of moisture that originates in the subtropics or tropics and forms these nice filamentary bands that extend from the tropical region into the mid-latitude or polar regions. And Christine's going to talk a lot more about these. These storms are extremely important for us. If we get a few of them, we have a wet year or an expected year. And if we have a blocking high pressure, like we've seen much of this year, those storms get deflected poleward into the Pacific Northwest and elsewhere. And that's the example on the right-hand side here. So the reason that storm, that plume of moisture is not hitting California or Oregon or Nevada is because there's a big high pressure system there. Next slide, please. And so when that high pressure is not there, we like that because that means that the storm door is open and we can have atmospheric rivers coming through one after another, making landfall. And we think about atmospheric rivers in terms of both moisture and moisture plus wind. So you need to transport that moisture into your region. And as you do so, you're able to generate orographic precipitation, which can squeeze a lot of moisture out of the atmosphere. Next, please. And there's a variety of other factors that control our interannual and even longer term weather and climate variability. And we call these other factors that influence them teleconnections, because we have this connection to conditions in the land, sea, ice, or in the atmosphere far removed from our region. A lot of that stems from the tropical regions, but also the polar regions as well. And these are important because they stack the deck, they change the odds of a wet or dry year, but they don't guarantee outcomes. So things like the El Niño Southern Oscillation, which corresponds to warmer or colder sea surface temperature anomalies in the equatorial Pacific, changes in Arctic sea ice, or changes in tropical thunderstorms can change the likelihoods of having a very stormy period or a very dry period. But again, they don't guarantee the outcomes. Next, please. But one concerning aspect about these teleconnections in terms of sea surface temperatures or sea ice is the way they change atmospheric waves, which bring us these low pressure systems that become associated with tropical and subtropical moisture in the form of atmospheric rivers, is a lot of the changes that we're seeing in a warming climate are pointing towards things that we don't really like. And one example of something we don't really like is the correlation between declining sea ice and a stronger ridge offshore of Western North America, which helps to block storms from making landfall and drives that moisture further poleward, keeping us very dry. Another example is in a warming climate, we're going to see changes in tropical convection, which is tropical thunderstorms, and that's going to drive increased precipitation variability, so more of that whiplash from very wet to very, very dry. Next, please. And so when we think about all of these different processes going on at all these different timescales, ranging largely from days to multiple years, but then carrying on throughout decades or centuries or even millennia, a lot of the landscapes that we see really result from just singular storms or even processes within storms, and they're not always climate. So it's important to recognize that what you see may be climate related, but it also may be a very impactful, bizarre, or extreme type of event. And that's one challenge with paleoclimate evidence when we try to interpret past climates, is disentangling whether it was a very large storm or a very wet climate. And that really highlights this interdisciplinary or multidisciplinary approach that we try to take to really figure out what is the driving factor. One good example of this is that we can still have floods and mass movements such as landslides or debris flows or avalanches, even in drought years, because they are driven by just a few minutes or a few hours of intense precipitation. So we can have a completely dry year and we can have one big storm, and you may misinterpret that, the sedimentary deposit, as being the result of a wet year when it was actually a very intense storm that took place in an otherwise drought year. So food for thought to think about when you look around at your landscapes around you. And with that, thank you very much. And I'll let Christine talk about atmospheric rivers and Dan talk about some seasonal forecasting next.
Thank you so much, Ben. That was great. It is my pleasure to introduce Christine Albano next. One of her areas of expertise is atmospheric rivers. Christine, tell us what's happening.
Thanks, Megan. And thanks to Ben, who already sort of introduced the concept of atmospheric rivers. And this is a term that you've probably heard a lot about in the past couple of days, and it's becoming increasingly used when we talk about winter weather in the Western US. And so in this presentation, I'm going to dig in a little bit more into the details of what these are and talk a little bit more specifically about why they're important. Next slide, please. So atmospheric rivers, which are also known as pineapple express storms, or ARs as I'll call them, are these long corridors of water vapor transport that extend from the tropics to mid-latitudes. And these are shown in this image as these sort of long filaments that are lashing out like a fire hose. And the colors here indicate the amount of water vapor, which is one ingredient of an AR, with the other key ingredient being wind, as Ben described, which drives the movement of these features across the globe. And at any given moment, there are 5 or 6 of these in each of the hemispheres, but they're particularly prominent in the winter. And that's because there is a greater temperature difference between the equator and the poles, which creates a pressure differential that sort of pulls air poleward. And it's through these narrow pathways that about 90% of all atmospheric water vapor transport to the upper latitudes is concentrated. And so these are very important features for our global water cycle. Next slide. And so this image is from earlier this morning. Oh, so go back. So this image is from earlier this morning, and we just added this little box here to show where the AR is making landfall along the coast as of this morning. And this is a rolling image of the 3-day period ending with where the AR was last night. And it looks kind of small and insignificant in this global context, but this is actually carrying a lot of water. And just to get a sense for this, the AR that's hitting right now probably has a flow volume in the range of about 6 Mississippi rivers worth of water. While some of the largest ARs that hit the West Coast are estimated to carry up to 15 or so Mississippis. Next slide. And so although these features are present all of the time, it's really when they make landfall that we sort of observe their impacts and really feel them. So here we zoom up into a close-up schematic of an AR as it's making landfall along the California coast. And one thing to note is that you can see that it's traveling at a pretty low altitude in the atmosphere. So if you're flying in a plane at sort of cruising altitude, which is typically about 30,000 feet, an atmospheric river is almost entirely below you, which I've always found to be sort of fascinating. And so when these rivers hit the coastline and interact with terrain, that water vapor is lifted up, it cools and condenses, and can result in very large amounts of rain or snow. This drawing is not to scale, but to give you a sense of the sort of anatomy of these features, they tend to be a couple hundred miles wide, so maybe half to 3/4 of the distance between Reno and Las Vegas, and several thousand miles long. So the distance between the California coast and Hawaii is about 2,500 miles, and these easily extend that far. Next slide. So one myth that I'd like to address about ARs is that these are often thought of as a coastal or California phenomenon. And while the coastal areas certainly take the brunt of the impacts, ARs are influential across much of the West. And this map shows different paths by which ARs make their way into and across Western landscapes, depending on where they make landfall. And as we go from north to south, we see that AR frequencies sort of decrease they decrease. But in the south, most of those that make landfall can actually travel pretty far inland because they aren't blocked by the large mountains of the Cascades and the Sierra Nevada. And these are a very important water resource for desert regions, including most of Nevada, which I will say based on my own research is not very well represented on this map. We know that ARs are important for the Great Basin in Nevada because we see high correspondence between precipitation occurring when these low latitude ARs occur and a greening of the Great Basin Desert in the following spring and summer, and we see that using satellite imagery. Next slide. So now I've covered some basics on atmospheric rivers, and I'm going to switch gears to talk about why they're important. And really their claim to fame has been that they are very strongly associated with flooding and other related hazards such as landslides and debris flows. And establishing this connection between ARs and flooding really provided the foundation and motivation for AR research, which is a relatively new field of science. We actually couldn't see these features in the atmosphere until about the mid-1990s when microwave satellite imaging became available. And it was not long after that that this connection to flooding was made along the California and Washington coasts. And this really spurred what is now 2 decades of focused research on this topic, especially as it relates to better forecasting these. Next slide. So just to further demonstrate both the widespread nature of their impacts and connections to flooding, this map shows results from a relatively new study that looked at the proportion of flood insurance claims that were associated with atmospheric rivers in terms of the cost. And the size of the dots indicate greater proportions of losses. And so what we see is that along the coast, really nearly all flood losses are associated with these events. And that amount tends to get smaller proportionally as you go inland, but they're still pretty significant in places like Washoe County, where we are here, and even Maricopa County in Arizona. Those 2 counties ranked 10th and 11th respectively as the counties with the highest costs associated with ARs. So one of the reasons we're really interested in understanding and better forecasting these is that they're really expensive. And we want to be able to better anticipate and mitigate against those costs. Next slide. So now that I've talked about how hazardous ARs can be, I'd like to debunk another myth, which is that all atmospheric rivers are hazardous. They actually aren't. In fact, most are beneficial. And it may surprise you to know that the AR that's occurring right now that we've probably heard a lot about is not the first one of the season for this region. We've actually had a couple of small ones already back in mid-November and December, and these have done a really nice job of gently adding to our snowpack, giving us at least enough snow to ski on, and they'll help our deserts bloom and recharge our aquifers this coming spring. Next slide. So our knowledge of and the public awareness of ARs has really increased greatly over the past few years. And because of this, there's been a recognized need to be more precise in our communication of what the impacts of a given storm might be. And this is one of the goals of this new AR scale. And this scale is similar in concept to the Saffir-Simpson scale for hurricanes in that it ranks ARs on a scale of 1 to 5, but it's a little more complex. The AR scale uses 2 metrics to determine the rank. The first is a metric called integrated water vapor transport, or IVT, which encapsulates both the wind speed and water vapor amounts and tends to be a good indicator of the amount of precipitation that will occur. The second indicator is that accounts for the duration of the storm, recognizing that the longer the storm is stalled, the more precipitation we'll get. So next slide. And so our storm today would be considered moderate in terms of its IVT, but because we're expecting it to stick around for a couple days, that pushes it up toward the strong category. Next slide. And so as a last point, and to reiterate some of the points that Ben was making about variability, these maps show the ARs that hit the coastline in 2019 on the left versus 2020 on the right. And we can see that although the number of ARs along the entire coast was about the same in both years, we had a lot more ARs that hit California in 2019, and we had more of them in the orange to red colors, indicating moderate to strong ARs. Next slide. And if we whittle this down to show just the strong ARs, we see a really big difference between the 2 years with, and this map shows the colors indicate precipitation amounts. And we see 2020 having much less. And this is really driven by the fact that we had fewer big ARs. So the presence and absence of these is really driving our year-to-year variability. Next slide. So to close, some of the main points I hope to have gotten across are that ARs are really important drivers of precipitation patterns and variability in our region. They have widespread impacts across the West, and they can be both hazardous or beneficial. And so I'm now going to turn it over to Dan to provide some more perspective on winter variability and forecasting for our region. Thanks.
Thank you so much, Christine. Very helpful. Dan McAvoy is a climatologist in search of the Holy Grail, seasonal forecast. He's going to debunk some myths for us. Dan?
All right, well, thanks a lot, Megan, and thanks for everyone for sticking around for the last talk of the night. It was great to hear Nathan and Ben and Christine, and I'll be integrating at least a few elements from each of their talks into my talk tonight, but I'm going to come a bit more from the perspective of science communication and specifically around seasonal winter forecasts. Next slide. And so the title of my talk there, it was motivated by what seems to happen every year around September or October around here, when everyone is kind of tired of the hot and dusty summer, looking forward to the fall and the winter. I start to get inquiries about what's going to happen this winter, and these inquiries come from friends and family. But as a climatologist for the Western Regional Climate Center, I also get quite a few requests from local and regional news outlets to talk about this topic. People want to know, is it going to be like 2019 Snowmageddon? That picture there on the left, I took, that's two of my kids and their friend in Truckee walking out to the swing set that's nearly buried, and the snowpack that's deeper than the height of the children there. So that was a big snow year in 2019. Or are we going to have a snow drought year like 2015, when we had pretty much hardly any snow throughout the entire winter? And in the early fall, we see the Farmer's Almanac come out, and people wonder if that's going to verify or not. And we hear a lot about El Niño and La Niña. That pops up a lot in the media, in the news around fall going into winter. People just really want to know, what's going to happen this upcoming winter. Next slide. But, is there really anything that is reliable in terms of making a 3-month forecast, say in November for the next winter? It's really all about predictability of our different Earth systems. And this graphic really nicely illustrates the level of predictability. And the vertical line, or in the vertical axis there, shows low to high predictability. And then on the horizontal axis, we have our time domain. And so higher predictability means that we get the forecast right more times than not. And so next slide. If we start with the atmosphere, and this is our weather patterns, our high and low pressure systems, the storm we're getting right now is a weather system. And so we're pretty good at predicting these weather patterns. The predictability is quite high, and you can see almost out to 7 days or so. And so the storm we're getting right now, this was pretty well forecast even a week ago. But that falls off rapidly after about 7 days. And once you get out to seasonal timescales, there's no predictability left. Next slide. And so the land surface now, things like ice cover, like Nathan was talking about, and snow cover and soil moisture, it varies quite a bit more slowly than the atmosphere. And so it holds a bit more predictability, out to several weeks or even a bit longer. There's some moderate predictability there in the land surface. And next, finally, we have the oceans, which are really the most slowly varying in terms of things like their temperatures. And so this is our main source of prediction for seasonal forecasts. And it was great to hear from Ben about the teleconnections that we have, because we rely heavily on this to make our winter forecasts. And I'll talk some more about those. Next slide. So the ENSO teleconnection, and I'm glad Ben mentioned that term. And so La Nina or El Nino, this is really our main source of predictability for winter in the Western United States. And so the ocean and the atmospheric patterns in the equatorial Pacific Ocean, they can have a really big impact on our weather locally in the Western United States and around the globe, really. And so these maps show the common weather patterns when the Pacific is in an El Nino state on the left, or a La Nina state, which we're in right now, on the right. And so the key driver to all this is the positioning of the jet stream or the storm track and where that sets up. And so these two maps show that during an El Nino or in a La Nina, the odds favor these types of weather patterns. And but this does not mean it will always end up this way. This is kind of the mean state during these La Nina or El Nino. And next slide. The important thing to note here, I've highlighted our area in Central California, Nevada there. Around Reno and Tahoe, we don't have a strong ENSO teleconnection at all. And so we're left out of being typically wetter or drier during these. And so that makes it even harder to forecast the winter. Next slide. So turning to what's going on this year, as I mentioned, we're in a La Nina right now, La Nina pattern in the Pacific, and it's a moderate strength La Nina. But when you're stuck in that land of no ENSO teleconnection, the La Nina numbers, the strength, it doesn't necessarily tell us too much about what to expect for the winter. And so this graph on the left, we're looking at the accumulated precipitation starting October 1st for several recent La Nina years within the last decade. And so this is from an average of 8 weather stations in the northern Sierra Nevada and the southern Cascades, shown on that map there on the right. And the first thing you notice there in the difference between those curves, there's huge variability from year to year, as Ben had pointed out. So 2016-17 was a weak La Nina, and that was the wettest year on record at this station, almost 100 inches of precipitation. The following year was also a weak La Nina, 17-18, and that wound up being below average and very similar to 2011-12, which again was a La Nina, but that was a moderate La Nina. And so this year we're tracking below all of those where they were at this point in January. And so we've started off quite dry, and we're currently at 38% of average as of yesterday. Next slide, please. And so the forecast from the Climate Prediction Center that was issued in November is shown here for precipitation. And it suggested slightly favored odds, or about a 33 to 40% chance of below normal precipitation for our region locally. And this is very much based on that canonical La Nina pattern I showed earlier, where the average state is about wetter than normal in the north and drier than normal in the south. But we're very close to that area of equal chances. And so the dry forecast there, again, is by no means a guarantee. Next slide, please. So what has actually happened so far this year? Well, prior to this storm, it's actually been a very, very dry winter thus far. We've had a few ARs, but no very strong ones. So on the left, I'm showing the snow water equivalent, or the snowpack, at a bunch of snow pillows in our region, and that's well below normal. They're all in that orange or red. You go further south in the Sierra Nevada, and we're getting close, pretty close to record low for this time of year. Then on the right, I'm showing the precipitation for the winter so far, which has also been very much below normal for our region. And so that forecast of below normal that I showed before is playing out somewhat with our region and the Southwest being dry. But if you look up into Montana, where the forecast was for above normal precipitation based on that La Nina pattern, they're not seeing that wet pattern. They've been very dry. And next slide. But things are changing this week, and we're currently in the middle of a major storm system. This is an atmospheric river, like Christine mentioned. And this will give our snowpack a really nice boost and possibly get us closer to average by the end of the week, but certainly won't fully bring us out of the drought we're in. But the bottom line is that we were able to forecast that storm almost a week ago, as I said, but there's no way right now of knowing the timing or how many of these large storms that we'll get several months in advance before the winter starts. And so this is why when I get asked the question in the fall about how snowy it will be, I have to answer, I really don't know, and then attempt to kind of go through what I just explained today. So next slide. Thank you. And that's all I got to wrap it up.
Thank you so much, Dan. I'm sure that's going to provide lots of questions. I'm going to kick us off with one. Here we go. I'm going to kick us off with one question to start. This is a question for all of you. And then while you're answering that, I'm going to go through the chat and look for some audience questions. So to kick us off, we're going to talk about a really practical application of weather forecasts, specifically when it's time to get outside and play in the snow. Where do you go for your weather forecasts, and what do you look at when you're looking at them?
Well, I can respond to that first. The place that I go to look at the most is the NOAA's National Weather Service. They have the expert meteorologists who that's their career, is forecasting the weather locally. And they have a lot of good websites and tools to get your local forecast. And in terms of going out in the snow or skiing, you really need to pay attention to things like wind speeds if you're a skier and want to go to the ski resort, to make sure the lifts aren't going to be closed. And then also the avalanche forecast in terms of snow safety while you're out there with the Sierra Avalanche Center around here will give you a lot of great information related to snow safety related to the weather conditions.
Awesome.
I'll second that. I go to the National Weather Service as well. I really like their Twitter page too, because they put some really nice infographics and tables and charts and really condense it to some nice information on their Twitter.
Yeah, I agree. It's definitely our local National Weather Service office is great. They do a great job and do a really good job of distilling the messages on social media. And I find that really helpful. When I'm looking for more technical information, I go to the Center for Western Weather and Water Extremes website. They have a lot of really great information about atmospheric rivers. It's comes in a more raw and sort of technical form, but they have the sort of best opportunity to get a really long-term view of what might be coming down the pipeline.
Ben, do you have anything to add? I was thinking about probabilistic forecasting. You're on mute, buddy.
So I use a variety of different atmospheric models, depending on what I'm interested in doing, that will kind of govern what I'm looking at. But in general, I look at the winds and temperature at the 10,000 foot level, because that's sort of a good reference location for most of the things that we get up to. That way you can tell, is it going to be really windy or not windy, and kind of govern your choices from there. And then for the more detailed things pertaining to precipitation, like Christine said, the CW3E site is really good. And then I'll use the Tropical Tidbits as a site that hosts a lot of different weather models where you can look at all kinds of different things for different regions and try to gather what's going on. And then I think it's also really important too to look at the observations before you go do something, because you can learn a lot about the weather by what's recently happened. There's the whole idea of persistence forecasting, where you're more likely to be right if you forecast what's been happening to keep happening. But understanding what's been happening can really help you understand whether the snow will be really good or may have gotten really warm and then frozen solid and may not be as nice, or whether it's going to be really cold in the valleys or really windy on the ridgetops.
That's super helpful. So I'm going to read a question from Alex now. Alex says, I've read from the ENSO, or the El Niño Southern Oscillation, phase only accounts for a percentage of local variability in weather patterns. So I'm wondering what other climate oscillations are relevant to seasonal precipitation and temperature variability. So are there other large-scale global patterns or large-scale teleconnections that influence us?
Yeah, it's basically an alphabet soup of different oscillations in terms of the ocean and atmosphere system, or sometimes just the atmosphere. Some of these oscillations are more statistical and not necessarily truly physical. So there is a little bit of caution advised in looking at these kinds of things. But some really important ones for us include the Madden-Julian oscillation, which is in reference to a sort of subseasonal oscillation of the location of tropical thunderstorms around Earth's equator, and how that migrates and ultimately changes the atmospheric wave patterns. That's, of course, strongly influenced by ocean temperatures. The El Niño Southern Oscillation is kind of one of our key ones. The Pacific Decadal Oscillation is one of these statistical artifact that seems to have some play a role to some extent, but that's kind of a whole another can of worms. And then there's things such as the Arctic Oscillation, or the also known as the North Atlantic Oscillation. But you could keep going down the list with all the alphabet soup, but there's many different patterns and processes. Typically these operate on the intraseasonal, so like 30 to 90 day timescales, and then upwards of multi-years towards decades in the case of the Pacific Decadal Oscillation.
Very cool.
And
Right.
I'll just
Yes.
add one thing to that that people might take interest to, is that there's been a lot of work in the last 5 to 10 years looking at the role of the ocean temperatures in the Northeast Pacific Ocean, where that blob, it was called, of really, really warm ocean water set up during the 2012 to 2015 or 16 drought. And so there's a lot of indications that ocean temperatures throughout the entire Pacific, depending on what time of year or where they are, can really have a big impact on our weather in the Western US.
There were a lot of memes about that. That's when I first remember seeing them. Elise has a question for Nathan. She's talking about that aerosol model. Can you tell us actually how you get that visualization, and then how you differentiate between different aerosols?
Sure. So I got that from NASA. So they really know what they're doing with that kind of stuff. And it's a really beautiful, beautiful simulation. So I think, as far as I understand how they made that, is that they take satellite data and they ground truth it. So they kind of have an idea of what's actually going on at the surface, and they combine all of it with supercomputers in a model, and that can actually predict what's being emitted and verifying that with the satellites. And then the model's also predicting how those aerosols are going to swirl around based on the atmospheric patterns. And so it's a combination of observations from satellites, observations from the ground, and modeling. So it's really quite a fancy simulation. So I'm glad they made it. Hope that
Very
helps.
cool. Yes. So we have a question from Lacey. I'm really interested to hear what you have to say about this one. So Lacey says, I often write about the impact of winter on wildlife. Now, we know from Christine that could be, impacts can be beneficial or harmful. She says, I often write about the impact of winter on wildlife, and I'm looking for neutral descriptive terms to refer to these severe winters. I've been told that calling them big winters is both unclear and too informal. How do you like to refer to winters like 1617 or 1819?
I guess I kind of think in terms of how many ARs and how many strong ARs. I mean, I'm probably biased in that way, but that seems to me to be a sort of objective way of describing, how much precipitation we have probably gotten in a year is by sort of understanding the strength and frequency of those events.
Yeah, and I was going to say it's very straightforward and simple, but just, a wet or a dry winter is quite easy. You could use the term severe, but that could mean wet or dry or warm or cold too. We have not had a lot of really cold winters in the recent past, so it's mostly about wet or dry, I guess.
Yeah, and one thing that makes it tough is that a lot of times a winter, it's hard to boil it down into just one word or even just a phrase, because it's very important, the timing of the storms. Like if all the storms come at the beginning of the year and then we go into a very, very, very long dry period, or if we have no precipitation and then we're ice skating on Tenaya Lake in the middle of January, and then it doesn't start snowing until March, or if things are kind of nicely evenly distributed throughout the year, which really never happens. There's basically all kinds of different combinations that can take place. And so I think it's tough to break it down into a simple description, a big year, or a small year, but kind of depends, I guess, what your key goal is, I would say, in terms of being as descriptive as possible is probably the most helpful way.
Fabulous. I've got a question for everyone. I'm sure you're going to each have a unique answer for this. What advances in your field do you look forward to in the next 5 to 10 years? And what does that mean for the rest of us?
I guess I can talk just really in general here for really big picture ice core research. One of the really hot topics right now is the hunt for the oldest ice. So they're down in Antarctica looking in little pockets, different little places, nooks and crannies to try to find ice that's over 1 million years old. And they've developed all sorts of tools to do this. They have a drill that'll go the whole way through the 2-mile ice sheet in a matter of days, just for the idea of getting down to the bottom as fast as you can. And so I think staying tuned for learning about ice-derived climate reconstructions going back over 1 million years would be something to keep an eye out from the ice core side of things anyhow.
I think it's kind of already happening, but it'll continue to happen over the next 5 to 10 years, is now that we're getting things like 30 or 40 years of satellite data from some of these satellites that have been up, like Landsat, being able to use those for climate analyses. Now you have climatologies basically to be able to look at departures from average from things like land surface temperature or the greenness of the vegetation. So you have long enough records to kind of compare it against other years. And that's it's becoming really exciting to see a lot of the new research that is being done with satellite-based climatologies. So.
Yeah, I'll just follow up from Dan's because I agree with that. I think what I look forward to the most is just sort of advancing our ability to manage and make sense of these huge amount of data we're collecting that can help us understand patterns and processes we see on the earth. And As Dan mentioned, we have satellites that have been collecting data for decades, and it's really only in the past 10 years that we've been able to deal with that amount of information in ways that are efficient, using cloud computing, for example. And our generation of data is sort of going up exponentially. And so there's going to be some catching up to do in terms of being able to use and analyze those data. And I look forward to sort of seeing how we're able to deal with that.
And then we'll have some other, hopefully new satellites going up in the coming years. There's a big NASA project to develop a snow-specific satellite, which will be really cool to give us a new perspective on spatially distributed snow and its duration and how much water is stored in that snow. And that'll be a really nice complement to a lot of these other longer term satellite records that now, as Dan and Christine mentioned, we have enough data and we're building the capabilities to analyze that data and come up with some really interesting insights. And I think the key point from that is it really shows the value of continued investments into our observations to keep them going, because the longer we have these observations, the more information we can glean about the past and what may happen in the future. And if we turn satellites off or lose weather stations that have been in a place for 50 or 100 years, we kind of lose that record and we don't get to keep it continuous in time. And that's really important to do so that we can better understand where we're going and how we may get there.
Very cool. So I'm going to combine two questions from Travis. This is for Nathan. Travis wants to know how the dirt layers got onto the ice core or into the ice core. And then for cores of ice that don't actually have organic material or dirt, how do you date them? How do you measure their age?
Yeah, these are good questions. So as far as the dirt in that ice patch that I showed you guys, that's really unusual. And we're still trying to figure it out too. But it definitely has to do with a combination of wind blowing a bunch of stuff onto the surface of the ice and then also melt. So you saw those two pictures in 2016 and 2018 from that ice patch. I don't know how long we stayed on that slide, but in 2018, you could see there was a lot more snow on top of it. And so as you build up that seasonal snowpack that might last for 5 or 10 years, it has all of the dirt that gets blown into that snow too. So in that seasonal snow, if there's a really warm few years and that whole seasonal snowpack that's sitting on top of the ice collapses and melts away, all of the dirt that's in that snowpack will also be concentrated onto the surface of the ice patch. So that's a combination of wind blowing stuff on to the top of it and then also concentrating by melting away the ice and leaving the dirt behind. And then as far as dating when there's not organic layers, so in a lot of ice cores, it's really easy to actually see an annual variability in the chemistry. And so for example, in Greenland or Antarctic ice cores, the sodium, which comes from the sea salt, goes up and down throughout the year. Really, it's really clear when you look at the signals from when the sea ice is really far out or the sea ice is melted away. So the ocean's exposed close to the ice core. And so you can know when the summer and winter is based on just the chemistry, such as like the sodium, the salt content. And then big picture, the big picture tie points for for ice cores are volcanic eruptions. So if you have a volcano that emits a bunch of sulfur into the atmosphere, that gets mixed around throughout the atmosphere and deposited all over Earth. And so all ice cores, not all volcanoes show up in all ice cores, but volcanic synchronization between ice cores, because volcanoes are such obvious events in the ice core record in the sulfur concentration.
Fascinating stuff. So we're going to take one more question. So Louise says, are atmospheric rivers a geologically recent phenomenon, i.e. since the Pleistocene, or have they been around for some time?
That's a good question. And I'm actually trying to remember back to some recent presentations I saw on this topic. I don't know, Ben, is that something you know? I mean, I know they've been around. They're obviously a Holocene feature of the atmosphere. But beyond that, I'm not sure.
Yeah, as long as we've had an atmosphere with moisture in it, dynamically speaking, they can take place. But over geologic time, the magnitude and location of them changes. And that's kind of what imprints the behaviors of the atmosphere onto the land surface, the sedimentary record, or the ice core records as well. And so we've always had them, always being a relative term, since we've had an ocean and an atmosphere that behaves somewhat similar to today. So probably hundreds of millions of years, I suppose. But their characteristics have certainly changed, and it's trying to use all of these geologic indicators of past climate, proxy data, or direct indicators that helps us try to reconstruct the atmosphere and climate system, and then try to understand, why did it look that way? How might things change if we start approaching one of those types of climate systems? Like, for example, there's a lot of interest in some of these much higher carbon dioxide environments as we keep putting carbon dioxide and other greenhouse gases into the atmosphere and warming our planet. What kinds of analogs can we use from past events? But of course, that gets complicated by some of these events took place a long, long time ago, when the continental because the continents were in different places and the terrain was different. So there's a lot of complicating factors. But overall, I think the answer to the question is, yes, they've persisted for a very, very, very long time, but they do change their characteristics with time. And that's kind of one of the goals, I guess, of a lot of our research, is to try to understand that. That was a really good question. Thank you.
Yeah, we have had so many good questions. There are a lot of scientifically minded people in this audience tonight. I am going to share one last thing. This is a plug for some citizen science. So some of you might want to actually get involved with research having to do with weather, climate, and water budgets. Here at DRI, we run a citizen science program. That means you can actually contribute to helping research. It's called Tahoe Rain or Snow. All you have to do to opt in is text the word winter to this number, and it signs you up. And it'll tell you how to participate, how to share information with us, and we'll send you alerts as to when the best time is to participate. So that's Tahoe Rain or Snow. Text winter to 855-909-0798. Right before we close, I want to give Patrick Turner, number one, the opportunity to tell us what's happening with the discovery and what we should come check out soon.
Well, we've got a number of things in the works. Of course, what we really need to do right now is get past COVID-19 so that we can be open to the public a little bit more. Just an FYI for everyone that's still listening, the museum is currently open Saturdays and Sundays, 10 a.m. to 5 p.m. And we're requiring advanced ticketing. So go to our website, nvdm.org, and you can get your tickets in advance. That way you can get in when you get there. One interesting exhibition that we're working on is a complete redo of an exhibition that we've had since the museum opened in 2011. The current exhibition is called Nevada Stories. We're redoing that and taking more of a natural history approach to our state's history and just calling the exhibition Nevada. But it will be a very interesting exhibition if you're looking to understand how our state has changed over time from a natural history approach. So keep an eye out for that. We're currently in the fundraising phases for that exhibition. But the best way to stay in touch with us is visit our website at nvdm.org, and you can sign up for our email list, and we'll keep you posted. One other thing, Megan, before I step off of here, I want to make sure that we thank two organizations that normally support this series, and that's Patagonia. We normally host these events at the store in downtown Reno, and so we're very appreciative of their continued support, even though we've had to move this to a virtual format. And we usually pour beer at those events at Patagonia from Imbibe Custom Brews here in town. And so we want to make sure we thank them as well. And I cannot wait until we can all get back to meeting in person and attending Science Distilled events at Patagonia and having a beer together, because these are fun, but it's a whole lot more fun when we're all together in the same room.
Second that. Can't wait till we can raise a glass together in person. Speaking of Nevada and speaking of COVID, save the date for the event on March 3rd. We have another virtual Science Distilled. We are going to be doing a 1-year look back on COVID research that is happening right here in Nevada. So a number of leaders from DRI, UNR, and Renown Health are going to be joining us for an in-depth talk of the COVID science and medicine that is happening right here in Nevada. So save the date, keep an eye out for alerts for that. And we just want to thank you all for your amazing questions. Thank all the speakers. Give them a little applause with your emoji if you can, to tell them that you appreciate them and all the hard work they do to keep us safe and informed during the winter. Stay safe out there. Take care, and we'll see you next time.
Bye, Megan.
Bye, Patrick.
That was a great discussion.
It was. They do a great job.